In architecture, grid-like elastic structures take the idea of minimizing the material input to an extreme, offering light constructions with huge spans. This is possible because they combine the structural advantages of both grid structures and curved shells. In this paper, we present a method for the design of such elastic bending structures. We compute a grid composed of elastic elements which are completely planar and straight. By fixing the ends of the planar elements to appropriate locations, the 2D grid bends and approximates the target 3D surface. Our approach can preserve the characteristics of the target surface well, and is even capable of handling non-convex surface boundaries. Our modeling pipeline consists of the following steps. Given an initial surface, the designer chooses a boundary curve on the surface. We compute an initial grid layout with a fixed number of members that can be provided by the designer. The grid is then optimized such that it approximates the target surface well when it is deployed. We then planarize the grid in an optimization process, while also taking into account fabrication constraints. Finally, the grid is ready for fabrication. We use the following representation of our geodesic grids. We parameterize the grid boundary with constant speed and curve parameter t in the interval 0 to 1, and represent geodesics on the surface by the t values of the endpoints. The geodesics between the points px and py with parameter values tx and ty correspond to a single point in a dual space, with the direction tx to ty also encoded. Here, two families of geodesics are represented in the dual space, with spacing and directions of members defining two sequences of points. If we extend the parameterization of the boundary to negative and positive infinity, the representation in the dual space is extended periodically. Since tracing the path of the shortest geodesic on the surface is computationally expensive, we instead compute the intersections between grid members using geodesic distances only, essentially treating the geodesics as polylines. To do this, we spread a distance field from each of the 4 distinct boundary points which serve as the endpoints of the intersecting grid members. By superimposing these distance fields, we can find the intersection between the grid members as the minimum of the resulting scalar function. In order to handle surfaces with non-convex boundaries, we need to identify curves that run along segments of the boundary which are non-convex. All shortest connections along the non-convex segment on the boundary are considered invalid for grid members. In the dual space, these curves constitute a square-shaped region, here depicted in red. Additionally, we identify curves that touch the non-convex segment on the boundary in one or more points, here depicted in blue and gray respectively. In the dual space, the blue curves emerge on the boundary of the gray regions, which themselves contain all gray curves. All curves in these regions are considered invalid and cannot be used as grid member curves. Because of these restrictions, the combinatorics of the grid can change during the grid optimization process. The main aspect of our work is finding networks of curves that nestle to the surface well when boundary conditions are enforced. As evident, some grids are better suitable than others, and their choice obviously depends on local surface features. To this end, we introduce 2 energies to find a suitable layout. To ensure a close approximation of the target surface but avoid costly physical simulation, we introduce an energy that estimates how closely a grid will preserve its initial shape when boundary conditions are enforced. To capture the surface characteristics well, we need 2 types of geodesics which must be present in our grids: least effort geodesics and most effort geodesics. We introduce a second energy to secure both such types of curves. The minimum of these energies corresponds to the layout we are looking for. Since arbitrary geodesic grids cannot be transformed to a planar state without changing the length of its members, we make use of the concept of sliding notches. This type of connection allows for a small amount of sliding at the connections between members, and thus provides 2 additional translational degrees of freedom at each connection. Finally, our elastic geodesic grid is ready for fabrication.